Good morning, grade 12s. All right, I have for you this morning one of my favorite lessons, of the course. So I actually really love. I went to the dentist this morning, and I was listening to someone else in another room who was talking, and they were saying how they were in university and they had like an organic chemistry class that they were studying for, and also a quantum chemistry class, and they hated the quantum and they loved the organic chemistry, but I'm exactly the opposite. I have always hated organic chemistry, and I really think quantum physics is cool. So, all right, and quantum chemistry, it's all connected. All right, so here's the deal, okay? Einstein won a Nobel Prize for this, and this was really one of his greatest achievements was figuring this out, okay? Yeah, and it's kind of connected to the way solar panels work and why you get sunburns and so on, like someone like me would get a sunburn. So here's the deal, the story so far goes like this. We've been looking at how we spent a few weeks looking at how light behaves like a wave, okay? And we have the electromagnetic wave model, which, as I've said many times, one of the greatest theories ever tested, which means that it makes all kinds of predictions, all of those which are true, okay? It changed the world. We developed this whole boom in technology as a result of it and everything. But turns out there's a couple of problems with it, okay? And here's where the story gets really interesting. So we saw yesterday that the way atoms emit light cannot be modeled using the electromagnetic wave theory. Okay, and you have to sort of treat instead of treating light like a continuous wave, you have to treat it as though it's tiny bundles, okay, that Max Planck called quanta. And these tiny bundles, okay, really are starting to, they don't bear any resemblance at all to a wave theory, okay? And so here's the deal. That's how black body radiation, that's all about how matter emits light, okay, and how atoms emit light. But now we're going to look at how atoms absorb light, okay? So atoms can do one of two things. They can emit light and they can absorb light, right? And when they do that, physical changes take place, okay, within the atom. So here's the deal. We're going to look at that this morning. We're going to look at how atoms, this is what the photoelectric effect is all about, how atoms absorb light, okay? Now here's Einstein's experiment, and I want to explain it to you. What we have over here, I think you can see my cursor, but what we have over here is a surface, and that surface is coated with sodium metal. So this little sort of light blue thing here is sodium metal. I can change it. I can make it zinc. It'll change the color, okay? Or I can make it copper and so on. Let's stick with sodium. Sodium, as you know, is alkali metal. It has a weak hold on its valence electron. And what our goal in this experiment is to hit the sodium with a beam of light, okay? And we have the sodium is on one plate of a coating on one plate of a parallel plate capacitor, okay? That's attached to this battery. We're not going to turn on the battery, okay? We're going to hit the sodium metal with a beam of light, and what we're trying to do is liberate its valence electron, okay? Now, in order to do that, we're going to try lights of different colors and so on, okay? Now, I'm just going to remind you of something that maybe is not obvious to you. So according to the wave theory, okay, wavelength is just the distance between two waves, right? Wavelength is connected to frequency. Okay, so if light is a wave, I have red light, let's say of wavelength 731 nanometers in this case. Yeah, that just means that's the distance between the waves would be 731 nanometers. Okay, and that wave would have a certain frequency, in other words, the number of waves per second associated with that. Okay, so by decreasing the wavelength, which I can do with this, I haven't turned on the light yet, by the way. Okay, it's at 0% output, but by decreasing the wavelength, I'm increasing the frequency, Okay, so I get more waves per second when I do this. Okay, and I can even go to ultraviolet, like that black light kind of. Okay, you get the idea. So this light is capable of emitting all the colors in the spectrum. I'll start with red at 736 nanometers. Okay, and brightness in terms of wave theory is the amplitude of the waves. So in other words, like, picture yourself sitting on a beach. Okay, it's the pandemic. There's waves rolling in, crashing gently on the shore. Okay, the distance between the waves, of course, is a wavelength. Now, the closer the waves are together, the higher the frequency, the more waves per second, right? So you get it, right? That's how waves work. Now, intensity, like brightness, would be how tall the waves are. So if you like surfing, then you would like, high intensity waves. You would like taller waves. But, if you're just swimming in the water, you want it to be sort of gentle, maybe you would prefer low intensity waves, okay? So now picture that, and what we're trying to do is use light waves to liberate electrons. Now electrons are like, picture them like, let's say we set up some beach chairs, wherever, and we put them in the water, okay? So that like you're not completely submerged, but you're just sort of sitting there on the shore and the waves are sort of crashing on the shore underneath you in your chair, okay? Now, if we want a wave to knock you out of your chair, what sort of property of the wave should we change? And the answer to that question should be obvious. It should be the intensity of the wave, right? In other words, make it taller. And a tall enough wave will knock you off. In fact, tsunami waves are quite tall, and they have very long wavelengths, okay? And they could knock a lot of people off their chairs, right? All right, so like, you get the idea. Waves, like, let's say I turn on this light, so watch out. I'm going to turn this on, I'm going to keep the intensity low. Okay, so here I'm trying this red light, and by the way, you'll be able to see the electrons in the simulation actually pass through the circuit and around this vacuum-like gap here and pass over to the positive plate on this side. Okay, and then there'll be current registering in here. But right now, there's no electrons being released. Now my light is only at 4%. Okay, so what should I have to do? Okay, what does the wave theory say I should have to do in order to release electrons? Well, I should make the light brighter. Does that make sense? Make it as bright. Let's try a little bit brighter. Nothing happens. Okay. Now what if I try really bright? Like what if I just crank it to 100%? Still nothing happens. Okay. Now right away, what you can't appreciate here is right away we're seeing a failure of the wave theory. Maybe let me explain why. Okay. We just made the waves as tall as we could. Now, somebody could say, well, maybe this light source isn't bright enough. Maybe we need something even brighter. Well, I'll tell you what. You can take a bright light source that's as bright as, it's so intense that it would melt the metal, okay? It would melt the sodium, but the sodium's not going to give up its electrons with this light, okay? So in other words, you're under a lamp so intense that it could actually melt metal, okay? Let's say it's incredibly bright. Yeah, the sodium's going to get hot, but it's not going to release its electrons, okay? All right, so right away, that's a failure of the wave theory. We should be able to knock some people out of their seats to liberate the electrons, okay, from the sodium. And all we have to do is make that light bright enough, okay? The color shouldn't matter, right? The distance between the waves shouldn't matter. Like if you're sitting on a beach, what does it matter to you if there's the waves are 5 meters apart or 6 meters apart? So if we change the wavelength, that shouldn't make a difference, right? So anyway, we can't, obviously it's not working with red, and I can try red of any wavelength. It never works, okay? There's no red wavelengths that are going to work here, okay? So what I'm going to do is I'm going to now change the wavelength until I see something happening. So I'm going to try shorter wavelengths, okay? So now I'm in the yellow spectrum, okay, around the mid 500s, and somewhere around here, okay, right there, at around 521 nanometers, all of a sudden it starts to work. Now it's so sensitive. If I go to 527 nanometers, Oh, it still works at 527, so let me see. Let's go to 538. 538 still working? Okay, so let me see if I can find the point where it stops working altogether. Okay, I'll try 552. 543 doesn't work. 535 works. Let's try 541, see if I can get it to sit there. 541 doesn't work. All right, so here's the weird part. Any wavelength longer than around 540 nanometers just doesn't work at all. Not at all. And it doesn't matter how bright you make the light source, it'll never liberate electrons from that sodium surface. Okay, but what happens is there seems to be a threshold. Okay, a threshold means there's a point, a specific number, okay, where it starts to work. And in this case, that number seems to be around 540. Now, unfortunately, I can't, oh, maybe I can. Let's try 540. Nope. Let's try 539. No. Oh, look at that. Okay, so the number seems to be 539 nanometers. Okay, so I typed in 539 nanometers for the wavelength, and look at those electrons just crawling across. Okay, so that's as bright as I can make the light source, and it starts to work. So in other words, like, here's the weird part. Let's say you're sitting in the beach, and these gigantic waves are coming in, okay, that are, let's say, 10 meters apart. They're huge waves. Easily should be able to knock you off your seat, right? Okay, so in other words, that's how bright our light is, but they can't knock you off your seat. Okay, but then more waves come in that are a little closer together. Okay, let's say instead of being 10 meters apart, they're 5 meters apart. Well, those ones can knock you off. And here's the thing, how do you use a wave theory to explain that? It makes no sense. Okay, it's not making any sense. It shouldn't happen like this. Why doesn't 540 nanometers work? It just doesn't. Okay, there's a specific number and it works. All right, so now we've seen already a major violation in the wave theory. Wave theory says that any wavelength should be able to liberate electrons as long as the waves have enough intensity. Okay, but that's not what really happens. What happens is only specific wavelengths will work. Okay, and anything longer than a certain threshold wavelength won't work at all, no matter how bright you make it. Like I said, you can torture that sodium with super bright light, bright enough to melt it. I mean, you put it right in front of, let's say, not sunlight, but something that bright that only emits red, okay? And it will never liberate the electrons. It'll melt, it'll fall apart kind of thing, but it won't liberate electrons, okay? It'll hang on to those valence electrons. Now, here's the thing also, okay? What if I turn down the intensity to make it even stranger? What if I turn down the intensity of my green light just down to 10%? So now, not only do you, does it still work, okay? And we can see these electrons still coming across. Okay, yeah, there's one, okay, there's more electrons coming here now. So it's still working, even when the light is dim. So that's even stranger, isn't it? Like here you are sitting on your beach chair, and these giant, like a tsunami wave comes in with a long wavelength. That can't knock you over, okay? But then these little waves of low intensity, so that means they're not very tall, just these little waves that are closer together, they knock you off your chair every time. And it doesn't matter how dim I make it. I can reduce it to 1%. It still works, okay? See, so the wave theory makes several predictions that don't seem to work here. Prediction number one, any wavelength should work, okay, if the light has enough intensity. So false. That's not what really happens. Only wavelengths shorter than a specific threshold work, okay? Number two, what is the effect of increasing the intensity? Well, if I increase the intensity, let's say I'm able to knock you off your seat and I make the wave taller, okay? What that should do is give you more energy. That's going to kick you off your chair with a higher speed, okay, if that makes sense. So what I'm going to do is I'm just going to see, you can see these guys are all getting kicked out, okay, by these little tiny waves that are coming in. So if I crank the intensity, make these waves really tall, you should be coming out with more speed, okay? So now I've cranked it to its maximum intensity, but you don't come out with more speed. So a tall wave should give you a big kick of energy, and you should be coming off of that metal with higher speed, but you keep the same speed all the time. What the effect of higher intensity is, more numbers of people get knocked off their chair, but they don't get knocked off their chair with any more speed, okay? And that contradicts the wave theory too. Taller waves should mean more speed, but instead it means more numbers. What should give more numbers is higher frequency, where you get more waves coming in to knock more people out per second. So if I decrease the wavelength, I should get more numbers being released, but that's not what happens. Okay, so let me change the wavelength again. So I'm going to go now. 539 is the threshold wavelength, okay, for this sodium metal. And what I'm going to do is I'm going to change it to blue. And we can see these ones that have been liberated by blue. What difference does it make to change the wavelength? Now I'm going like above the threshold or whatever, so, or shorter than the threshold wavelength. And these ones, you can see the green ones are still moving quite slow, the ones that were liberated by green light, but the ones liberated by blue light move a lot faster. Okay, so here's the deal. Changing the frequency, by increasing the frequency of the waves, I should get more numbers being released, but instead I get more speed. Okay, not more numbers, but more speed. And by changing the intensity, I should get more speed, but instead I get more numbers. Okay, so if I decrease the intensity of blue light, it's still going to work, but I just get fewer numbers. Okay, but everybody has the same speed. So it's this weird contradiction, guys. It's so bizarre. So what's happening is changing the amplitude of the waves gives you more numbers, and it should give you more speed, but it gives you more numbers. Changing the frequency of the wave should give you more numbers, but instead it gives you more speed. It's like this weird contradiction, okay? And there shouldn't be a threshold at all. So why does 539 work? For this, 539 nanometers for sodium, but not 540, like, are you kidding me? And even 539.1 wouldn't work, okay? It's that specific. It comes down to a specific number, okay? An exact number. Now I want to show you something else. I'm going to change this to copper, okay? And with copper, if I change the surface to copper instead of sodium, see what's the difference? You know the chemical difference between sodium and copper. Copper is a transition metal. Sodium is an alkali metal. Alkali metals are notorious for having a really weak hold on their valence electrons, what makes them so reactive. Copper, though, is stable. It's almost inert, right? It's a transition metal. It's multivalent, okay? And we use it for, making conductors and stuff like that. Yeah, the blue light won't liberate electrons on the copper, okay? So remember, our threshold was 539 for the sodium. So if I go back up there, if I just type that in, 539, yeah, that doesn't work at 100% for copper. And in fact, if I were to find something that works for copper, I'm going to have to keep going here until I'm now into invisible wavelengths. And right there, let's see what the number really is. 245 works. 246. 246 works. 247. That's still working. Let's try 250. Yeah, that works. 260. Boy, I thought I was close. 260 still works. 270. 270 doesn't work. Okay, so 270, it stops working. So let's see if we can narrow that down. I'll try 265. Nope. Let's try 262. Yes, 262. Let's try 263. 263 works. Let's try 264. And 264 doesn't work at all. So the magic number for copper, 263. So what effect does changing the metal have? Well, that seems to change what the threshold is. So for sodium, the threshold frequency, or sorry, the threshold wavelength was 539 nanometers. Well, for copper, it's 263 nanometers. Okay, so no wavelengths longer than 263 nanometers, including all visible wavelengths, can liberate an electron from copper. Okay, so copper seems to have a different threshold. Otherwise, all the other rules seem to work the same way. So if I change the intensity, that changes the numbers that get liberated. So now you should still see some being released at this low intensity. Yeah, okay, so they're just coming off like a little bit slower. Okay, we don't want to wait too long. So I'm still getting some emission, just not as many per second. And if I change the wavelength by making it less, that should increase the numbers because I get more waves, per second. But instead, what it does is increases the speed. Okay. So here we see another catastrophic failure of the wave theory, and I think it's really clear here. Okay. The wave theory just doesn't work. So when you're looking at how atoms emit and absorb light, wave theory makes several predictions on what should happen in this experiment. They're all wrong. It's all wrong. And so whatever's going on here, light is just not behaving like a wave. Now, I'm going to take a moment here. I'm going to pause this. Let's take a moment and think about Planck's hypothesis. Okay? Planck said that if we treat the light not as so much a wave, but as a bundles, and each bundle has a certain amount of energy. So bundles, they called quanta, right? And if you remember, it goes hc over lambda, okay, is the energy per bundle. Well, the thing is that if light is really a bundle, a little bit of energy or whatever it is, and not really a wave at all, okay, when you think about it, well, then this starts to make sense. Okay, because what's the difference between a red bundle and a violet bundle? Well, the red bundles have less energy per bundle because when you do Planck's equation, you get so many electron volts. We did it the other day. Okay, so there's, I think it was around 2 electron volts per bundle, whereas blue light had 4 electron volts per bundle. It has more, right? Something I can't remember the numbers exactly, but yeah, you'd have to plug in the wavelength and you can get the energy per bundle. See, so the blue and the violet have higher energy per bundle, okay? Now, in order to liberate the electron from copper, your bundle has to have a minimum amount of energy, okay? And so that minimum amount of energy seems to be associated with that number around 263 nanometers. Those bundles have enough, but 264 nanometers don't have enough energy to liberate the electrons. Okay? Now, what if we shorten the wavelength even more? Well, then those bundles have even more energy. And so the electrons get more speed because the bundle first liberates the electron. It gives the excess energy to the electron in the form of kinetic energy. And so it goes faster. Now, what about increasing the brightness? We got more electrons being released. Well, the thing is that we're not making the wave taller when we increase the brightness. What we're doing is we're shining more bundles. Okay, so a brighter light is not taller waves, okay, in this model. A brighter light is more quanta. It's more bundles, okay, packed into the beam. And each bundle can liberate 1 electron. So if you put more bundles per second, that's going to liberate more electrons per second. So what you have to get here is we have to completely abandon the wave theory to get this. You basically have to completely abandon the premise on which the wave theory is built is that light is a wave. Well, there are no waves here. Okay, in this experiment, in Einstein's photoelectric experiment, it's extremely clear. There's no wave activity here from those sources of light. You can only explain what's happening by looking at these things as particles. Now, eventually a scientist, I don't think it was Einstein, changed the name of the quanta of light to a photon. And a photon is a particle of light. Okay, so this is getting really bizarre because we've seen in several experiments how light behaves like a wave, but not this time. Okay, not with black body radiation and not with the photoelectric effect. And it's very clear it's not behaving like a wave here. Okay, so we've got a major problem with our wave theory here that's manifesting itself in how atoms absorb and emit light. So now this video, I hope you watch this because it's a really important to get the experiment. Now I'm going to go back to the notes and create a second video. I've said a lot of things here, so I'm going to go through that second video with the notes kind of quickly. And there's an equation that goes with Einstein's thing here, and the homework is based on that.